Okay, so two basic problems here with the way people did the problem. First of all, the first thing you do is you look at what's changing. This is a product of two things that are changing. This is a product of two things that are changing. This is a complicated function of something that's changing. Obviously, the terms that are nonlinear are VCAN, VCA, and KCA squared over 1 plus K prime CA squared. Those three terms are nonlinear. I would say out of 33 people, only 5 or so even understood that these terms were nonlinear. Is there something mysterious about this? The first thing you do, which I did in class, when you write down a problem, is you circle the terms that are changing, the factors that are changing. And when there's more than one of them in the same term, that means it's nonlinear. So this has to be linearized. So when you linearize VCAN minus CA, that's VCAN minus CA at the reference, whatever the reference state is, plus the derivative. This is a function of two variables. F of x and y is f of x0, y0, plus the x at 0 times x minus x0, plus the f dy, 0 times y minus y0, plus nonlinear terms. Here, x is v and y is CAN minus CA. The derivative with respect to v is just CAN minus CA. At the ref, times v prime. And the derivative with respect to CAN minus CA is just v times CAN prime minus CA prime. Plus nonlinear terms. Out of 33 people, maybe 2 people got this right. We did this in class on the blackboard. There's a problem with people understanding what's going on in class, and if they don't, asking to have it explained until they understand it. I can't read your mind. If you don't understand something, you have to ask. The next thing, and this I found quite shocking, this is a nonlinear term. This term is nonlinear. CA squared is nonlinear, but CA squared doesn't appear on its own. It appears in this term. So this term needs to be linearized. So this is linearized. It's KCA squared over 1 plus K prime CA squared at the reference state, where CA is the value at the reference state, plus DDCA of KCA squared over 1 plus K prime CA squared at the reference state times CA minus CA ref. And you just got to take the derivative, which is the quotient rule, which you learned in high school. You know how many people, half the class, said, I don't feel like doing this. I'm going to linearize CA squared and say that's equal to CA reference squared plus 2CA reference, CA minus CA reference. Well, that might be nice if CA squared appeared on its own in the equation. It doesn't. You can't plug this in here and here. In fact, if you do that, you get something that's still nonlinear, because you've got a CA prime in the numerator and a CA prime in the denominator. That's still nonlinear, and it's wrong. It's simply wrong. Just because someone doesn't like taking derivatives using the quotient rule, which you learned in freshman calculus, and if you took calculus in high school, you learned it in high school, doesn't mean that you can do something else and make up a different problem where you have a KCA squared. That's not what I asked. That wasn't the problem on the exam. This was, I found, shocking. I could understand if you wrote this and you didn't really want to go through the details of doing the derivative because you were running out of time. Fine, at least you write this down and say this is the right way of doing it. But to do this, when there's no CH squared appearing by itself in the problem, is telling me that you're having a problem with basic math, basic calculus. Just as this tells me you're having problems with basic math, and just as this is telling me that you're having problems with basic math, understanding what a nonlinear is. And those are things that are long before this course. This course assumes that you know basic calculus, that you know how to take a derivative. This assumes that you know what nonlinear means. That you realize when two things are multiplied by each other and they're both changing, that's nonlinear. These are things that you're assumed to know before you walk in the door of the first day of class. Finally, on the third problem, you were given the following. This is Q of the heater as a function of time. And you were told that, say this is 0, that when the heater goes on, it starts out going on linearly. It doesn't, in class we had a problem where it was just a step function, it went on. Here it doesn't go on linearly, it goes on linearly. And then once it reaches its maximum, Q0, it stays constant for a while until the temperature happens to go too high, and then it gets turned off, but it doesn't turn off instantly. It turns off also with a straight line, like this. And once it turns off, once it goes to 0, it stays off for a while until it turns on again. So this is what you were given. I'm just graphing it. I'm just graphing this, but this is what you were given in equations. And the slope of this was 1 over theta 1. And the slope here was minus 1 over theta 2. That was given. So this is just graphing. I just graphed it. So clearly, theta h, QH depends on time. See, T depends on time. It changes with time. It's not just a step function. In class, it was a step up and a step down. So for each regime, it was independent of time. In this problem, explicitly it depends on time. This was Q0 times T over theta 1. This is 1 minus T over theta 2. It depends on time. So when you write out the equations, we had an equation be theta dt, where theta is the temperature. So it's a bad choice of notation that I call these thetas. We had plus theta over some time constant, which is the same one we had in class, was equal to something with a QH here. QH is a function of time. I think I had another term here, which was theta of theta the outside temperature over T. Because you have heat transfer through the walls, so you have theta outside minus theta. This is a function of time. I would say most of the class that even got this far used the equation. We have the equation for dy dt plus ay is equal to b of t, b. And we had two equations, reference equations in class. One where a and b were constants, and one where a and b were functions of time. Clearly, q is a function of time. You have a t here, it's explicit. 80% of the, or 90% of the students that even got this far decided to make q a constant because they were just copying out of their notes without thinking. They were just copying out of their notes the problem that we did in class. And that's the problem when I make an open book exam, is that people just copy stuff out of their notes and they don't think about what they're doing. So this was, I really can't understand that. I really can't understand that people didn't realize this is a function of time when T was explicit. Now, maybe I should have written this up here, theta dt plus theta over t, theta outside over t, plus QH of t. Okay, and when I ask what's going on here, so the temperature of the room, theta of the room versus T. Well, I wanted you to reason what was going on. So let's say this is 17, when the temperature, let me make this a little longer. Versus T, when this goes on. Well, we know that if it went on as a step, then the rate of increase in the temperature from what we did in class would be exponential. But it didn't go on as a step, it goes on as a ramp. So that's slower. So the temperature does not rise exponentially, it rises slowly. It's not linear, it's not exponential, it's something in between. It's a slow rise. When it gets to this point, it's a constant. So now it starts getting faster. Now it starts going exponentially. Exponential. Now over here, when the heater goes off, and let's just make this correspond here, it's much faster. So this goes up slowly, and then from here it goes up exponentially. And now, when the heater turns off, it doesn't turn off instantly. It takes time for it. It's still producing heat. It's still producing heat. So it's producing less, but it continues to go up. Just slowly, because it's still producing heat. Until it gets here, where it stops producing heat. However, at some point, the heat it produces isn't enough to continue heating the room because I have losses through the wall. I have losses through the wall because it's cold outside. So at some point, this started going up, but then it eventually turns over and maybe starts going down. And down here, it now starts decreasing exponentially. It's going down slowly here because I'm still producing heat. And here it's going down exponentially. So this is exponential, and this is exponential. But the rest of it, this is a slow increase, this is a slow increase, and this is a slow decrease. And eventually, it overshoots. It can overshoot. It goes down and it can get below 17. Because when it hits 17, the heater gets turned back on, but it starts out producing zero heat. It only produces a tiny amount of heat. So eventually, it comes and starts going back up and gets above 17. But I have overshoot here and I have overshoot here, where this is 23. I have overshoot on both sides. And I can do this without writing down equations. This is just reasoning from what's going on here. I don't need to solve any equations. When you solve the equations, you find it. The other thing, which I emphasized multiple times, is every time something changes, the region changes. This is region 1, this is region 2, this is region 3, and this is region 4. And in each region, I need to solve the equation anew. It's a different system because QH has changed its behavior. And if this is T1, this is say 0, let's call this T1, this T2, this T3, and this T4, in region 1, everything is a function of T minus T1. In region 2, everything is a function of T minus T2. In region 3, everything's a function of T minus T3. And in region 4, everything's a function of T minus T4. And when I say everything, I mean theta. The temperature is a function of those quantities. every concept here is something we did in class. Except for this detail, which I wanted you to be able to reason from this. Okay, so what's the upshot? The upshot is the performance on the exam was uniformly poor. Poor, not fair, poor. Even the top grades, the people did something sensible on one of the three problems. And two of the three problems, there was nothing sensible. So that's concerning, because when you graduate and you go to work, you need to know control. More importantly than knowing control is you need to be able to think about problems when you're under pressure. When you're on your job and your boss comes in and says, we have a problem, you need to solve this, you can't start writing down nonsense. You're not going to keep your job that way, and that's independent of this course. When you're under pressure, you still have to make sure you're writing down sense and not nonsense. When you need to see if something's nonlinear, you can't write down mathematics that makes no sense. When you need to figure out what's nonlinear, you take your pink chalk and you circle the nonlinear terms. And you don't say, I'm just going to make up my own problem. I'm going to make up a problem where I can linearize CA squared. There is no CA squared alone here. It's CA squared over 1 plus K prime CA squared. Similarly, in part B, which was extra credit, so I give the whole 40 points for just part A. For part B, with a temperature change, in this term, so I have K0 e to the minus P over R theta CA squared over 1 plus K0 prime e to the minus E prime over R theta squared, theta CA squared. This is a function of both CA and theta. Both of them are changing. There's my pink chalk. As theta changes, CA changes. So when that happens, f of x, y, I think I did that right here. Here it is. I don't have to rewrite it. So I have this quantity, it's RA at the reference date. This is RA. Plus the RA, the theta at the reference times theta prime, plus the RA, the CA at the reference, CA prime. And it's exactly this formula. So you got to take the derivative of this thing with respect to theta. Even if you don't want to go through the details on the exam, you at least write out that that's what I'm supposed to be doing. Evaluate at the reference date times theta prime, and then the derivative of this with respect to CA squared with respect to CA, which is what we did in part A. So we know what that derivative is already, times CA prime. So these are issues that I am very worried about. I'm very worried that people are not learning the material, and the way you learn the material is by doing the homework, and that when you're not understanding it, you're not asking. As I said right from the beginning of the semester, I am happy to have review sessions where I solve problems on the blackboard. You just have to ask. I'm not going to set review sessions where no one shows up if no one asks. I'm happy to do it if people are going to show up. So you have to realize what you understand and what you don't understand. And then you have to ask if there's a problem. Are there any questions? Were you able to record from the beginning or you got here late? Because that one's also recording, but there's no reason for both. Huh? You stop. Okay. Are there any questions? I would like you to take a deep breath and think for a minute, and I would like you